Hello all, myself Dr. Avik Pradhan, Assistant Professor, Department of Mathematics, School of Basic and Applied Sciences, Adams University. Welcome to this lecture of the series. We are talking about the basics of probability theory. So in last few lectures, we talked about the basics of set theory. We discuss about the things related to basic definitions related to the probability. We talked about the sample space. We talked about the event. We talked about the axiomatic definition of probability. So today we are going to talk about the axiomatic definition and the probability assignment. So let us look back into the axiomatic definition. The axiomatic definition says that if we have a random experiment and corresponding to which we have a sample space omega and script s, then probability will be a measure, or probability is a set function from the sample space to the real number set, which satisfy the three axioms. First axiom is that probability of any event is positive, non-negative. That means greater than or equal to 0, which is the axiom of positiveness. Second axiom says that probability of sample space or the set of all possible outcomes is equal to 1. That is the axiom of certainty. And the third axiom is saying that if we have a sequence of mutually exclusive events, then the probability of union of the events will be equal to the summation of the probability of individual events. So this axiom is known as the countable additivity. So any set function from the sample space to the real number set which satisfy all of these three conditions is a probability measure. Is a probability measure on the sample space corresponding to a random experiment. And these three things, the set of all possible outcome omega, the sigma algebra corresponding to the sample space, that is script s, and the probability measure p, which is a set function, together this triplet is called the probability space. So let us take an example that suppose we are considering considering the experiment of tossing a coin, then the set of all possible outcome omega will be the head and tail. Script s, which is the sigma algebra corresponding to it, is going to be phi, omega, singleton h, and singleton t. So this is so together this omega and script s together will be they are the sample space corresponding to the experiment. Now if I define a function p, which is from this this sample space or omega to the real number set, defined by probability of h is equal to 2 by 3 and probability of t is equal to 1/3. Then this definition, whatever I have mentioned here, is it satisfying all the three conditions or the three axioms of the probability? That means the question is that is this definition of probability, or is this definition of function, can be considered as a probability of the probability measure of this experiment? The answer is yes. I can take these values at the probability of h and probability of t as 2/3 and 1/3 respectively. They all are greater than or equal to 0. So any event, if I consider suppose probability of pi, which is will be equal to 0, and probability of omega, which will be equal to 2/3 plus 1/3, so that is equal to 1. So all the probability of all the events corresponding to this experiment is going to be greater than equal to 0, and probability of omega is equal to 1. And if I take any two disjoint sets like H and T, then the probability of union set is going to be the sum of the individual probability. So this definition of the function will be a probability measure. In fact, in general, if I take the probability of H equal to small p and probability of T equal to 1 minus p, then that also satisfy all the three criteria, and that will be a probability measure corresponding to that. So basically, here I am not assuming that the probability of head is equal to half, probability of tail equal to half. That is one kind of assignment which can be considered as the probability of the events. So I can take in general any value between 0 to 1 as the probability of event corresponds to getting a head in a toss of coin. And similarly, I can define the probability of T in that case also. So it is not necessary that I can take the probability of H equal to half. Then there may be question that then why we take the probability of head is equal to half. That answer to that question is related to the assignment of probability. That is the next thing we are going to discuss about. Let me erase this. Okay, so let us go to the assignment of probability. So there are three approach or three way to assign probability of an event. The approaches are the classical approach. Second is the relative frequency of occurrence or the statistical approach. And the third approach is the subjective probability approach. The first thing, that is classical approach, also sometimes referred as classical definition of probability in the literature, and the relative frequency of occurrence or statistical approach is referred as statistical definition or empirical definition of probability in the literature. And the subjective probability is also an approach to define the probability of an event. So we'll first go for the classical approach, that is uh, here. The classical approach was introduced by Laplace in 1812 in his article Theory Analytic Does Probabilities, in which he mentioned that if we have a discrete sample space omega or a discrete set of all possible outcomes, say means discrete set, and contains at most n number of points, which is finite, then we can define the probability of, or we can assign the probability of an event as the ratio of occurrence of that particular event to the total number of possible outcomes. That means if I consider an experiment where the sample space or the set of all possible outcome contains n number of sample points, then probability of an event A is equal to number of favorable outcome M divided by total number of outcome N. So that I have mentioned that thing here, that probability of A is equal to M by N, where M is the total number of possible outcome in favor of sorry, there is a mistake. It should be M equal to total number of favorable outcome. It should be number of favorable outcome, favorable outcome for A and this will be, this n is going to be total number of outcomes. Total number of outcomes. So basically, this will give you the ratio which is less than equal to 1, and it is obviously greater than equal to 0. So let us try to understand this thing by using an example. So here we have taken example. What is the probability of getting exactly 2 heads in 3 tosses of a balanced coin? So if I consider and if I consider this experiment, then the sample space or set of all possible outcomes, if I consider the omega as, so omega is going to be containing 2 to the power, so exactly 2 heads in 3 tosses. So I'll have 2 to the power 3, which is 8 possible outcomes will be there. So the outcomes can be written in this manner. So I can write omega is equal to head, 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 tail, head, tail, head, head, tail, head, head, tail, tail, head, tail, head, tail, um, head, tail, tail, and tail, tail, tail. So there are 8 possible outcomes for this omega. Now, the event is that there will be exactly 2 heads in the 3 tosses. So if I consider A as equal to exactly 2 heads, exactly 2 heads in 3 toss. So what are the possible outcome for this, favorable outcome for this event? So that will be exactly 2 heads. So I can take H, head, head, tail, head, tail, head, and tail, head, head. So these are the only possible outcomes which are in favor of the event A. So we can take, according to this assignment of, means according to this approach, we can assign the probability of A as equal to the number of favorable outcome, that is 3 here, divided by total number of outcome, which is 8 here. So the probability of A will be equal to 3 by 8. Okay. So in gist, we can say if we have finite number of outcome for a certain experiment, random experiment, then we can assign the probability of an event as the number of favorable outcome for the event divided by total number of outcomes. Now here actually how we are assigning the probabilities, here one assumption is that all the outcomes for the experiment are equally likely. That means if I have n number of possible outcomes for the experiment, then probability of occurrence of an individual outcome is going to be 1 by n. So here, how we are defining this probability, we are thinking this probability as probability of the event A is equal to m favorable outcome, and each outcome is equally likely as 1 by m. So that is 1 by n. That is equal to m into 1 by n, which can be written as m by n. So for an event A, if there are m number of favorable outcomes, for each outcome, the probability of occurrence is equally likely. That means 1 by n. So I can think that those m possible outcomes can be obtained with chance of m by n. So that is the classical approach to uh, assign the probability of an event. Now the thing is that in this approach, the limitation is that there are 2 assumptions we have considered. One assumption is that the number of outcomes for the experiment is finite, that is n we are considering here. And the second assumption is that we are considering the all the outcomes of the experiment are equally likely. But in reality, we may not have that kind of situations. So these are the two limitations for this approach. One is we are considering the finite number of outcomes for the experiment, and the second is the assumption of probability of occurrence of a particular outcome is equally likely. So these two things may not happen in the reality. So we have to have some other process or other approach to define the probability where we have countably infinite or uncountable state as the sample space or the set of all possible outcome as the for a random experiment. So we need to develop some other way which can helps us to assign the probability of a experiment where infinitely many points or infinite uncountable number of elements are there. So that approach is known as the statistical approach. So let us go for that one. Relative frequency of occurrence or statistical approach. So in this approach, we need not to consider that assumption of equally likely, or we need not to consider the assumption of that uh, countably finite, means countable set or finite set. We need not to consider that assumption in this case. So what does this approach says? It says that if a trial is repeated a large number of times under essentially homogeneous and identical conditions, then the limiting value of the ratio of number of times the event happens to the number of trials, as the number of trials becomes indefinitely large, is called the probability of happening of the event, provided limit of the limit of this limit exists finite and unique. This definition was given by von Mises. So it says that I can define or I can assign the probability of an event as the limiting value of the ratio of number of times an event occurs to the number of trials we consider. And as the number of trials becomes infinitely large or indefinitely large, that limiting value will actually represent the probability of the event. So mathematically, we can think as if I have n number of trials of the experiment, and in those n number of trials, m number of trials shows in favor of the event, then the probability of happening of that particular event will be equal to limit n tends to infinity m by n. So basically here we have this is also called the limiting definition. So here we are taking n as indefinitely large number. It represents the number of trial which is conducted as the infinity or a large number. So here you can think this as the frequency also. So if n is considered as the total number of frequency or total number of times we repeat the experiment, and m is representing the frequency of that particular event. Okay. So let us try to understand this thing in elaborately. So here with the example we are going to understand this thing. So here I have taken that omega is a discrete set. That means that set of all possible outcomes is a discrete set, and it contains a finite. It contains a countable number of points. Then, if it is a discrete set and countable number of points are there, which is finite, then we can say that probability of an single sample point or single event as a equally likely event. So we can assign the probability of a point as a equally likely point. So if I have uh, a number of sample points in the set omega, then we can assign the probability for individual point as 1 by n. But if I have a set which is discrete, countably infinite, then we cannot assign probability for each and individual sample points, because I have infinitely large number of sample points. So if I give that 1 by n in that case, that means 1 by infinity, then the probability of individual points will be equal to 0. So we cannot assign in that manner, means in the classical approach, whatever we have considered, we cannot use that approach here. So in this case, how we assign probability to the event? In this case, we assign the probability to the event as the summation of probability of individual points where the point belongs to the set A. So here we are not assuming that all the sample points are equally likely. We are taking the sample points which are in favor of the event A together, and we are assigning probability of that event A in a in the together manner. So here we are not assuming the equally likely concept whatever we had in the classical approach. So this equally likely assignment we are not considering in this case. Okay. So for example, you can take suppose I have omega, which is an infinite set, countably infinite set, 1, 2, 3, 4, 5, 6, up to infinity we have. Then it is the set of positive integers or natural numbers. Then if I consider the sigma algebra is going to be the fifth case, which is set of all possible subsets of omega. We can define probability of an individual point as 1 by 2 to the power I, and I is equal to 1 to infinity. So first question is, can I assign the probability in this manner? So if I assign the probability in this manner, then the total probability must be equal to 1. And this probability is greater than equal to 0. So obviously it is following the first axioms of the definition, axiomatic definition. Now the only thing we have to check is that whether the total probability, that means if I take the summation of this, if I take the summation of this I, whether it is equal to 1 or not. That is the question. So let us try to find these things. Suppose I'm considering summation of pi. So that is equal to summation of 1 by 2 to the power I equal to 1 to infinity. So let's say we can consider this as a geometric series. So we have a by 1 minus r. So first term is sorry. So this will be equal to, first term equal to 1 half. The second term, so first term is equal to half. Second term is 1 by 4. So the common ratio is half again. So 1 minus r is equal to half. So this will be equal to half by half. That is equal to 1. So the total probability is going to be 1. So if I consider the sample space omega, so if I'll have probability of omega is equal to sum of all these things. So this will give me 1 here. So this assignment of the probability is valid. So it is satisfying all the axioms of the axiom of the axiomatic definition. So in this manner also we can define the probability. Remember, here we are not considering the assumption of equally likely events, or we are not assigning the equally likely probability to all the individual sample points. We are giving the probabilities in a different manner. Okay. Okay, so let us see one more example. So in the last example, we have considered the countably infinite set, where the set of all possible outcome is countable set but infinite set. Let us consider an example where the set of all possible outcome is uncountable set. So we are considering omega, which is a uncountable many points are there. Uncountably many points are there. So for each 1 point set, which is an elementary event or the simple event, in that case, we cannot use the concept of equally likely assignment of probability. So in this case, I have infinitely many points. So if I put equal likely probability for each and every elementary event, then it will actually not follow, or it will violate the second axiom of the axiomatic definition. That means probability of the omega, probability of this sample space is not equal to 1 in that case, because in the set omega we have infinitely many points, which is actually uncountably many points. Okay, so in that case, how we can assign the probability? In this case, one assigns probability to compound event consist of intervals. As I already mentioned, that we have two type of sample space. One is discrete sample space and the other is continuous sample space. For the discrete sample space, we have the sample space which is countable. For the discrete, for the continuous sample space, we have the uncountable sets. So in that case, we present the sample space as intervals. Now, so if we want to assign the probability in this case, then we assign the probability to the compound events which are represented by the intervals. So if I here I have considered an example that if I consider an experiment for which the sample space or the set of all possible outcome omega is given by the closed interval 0, 1, and the sigma algebra is given by Borel sigma field, which is the Borel sigma field, or for all the subsets of omega, then the assignment of probability for an interval, this is a subset of this closed interval 0, 1, will be the length of that set. Okay, then where this I have considered this event as in the set which is the interval I, then the probability of occurrence of that interval I will be equal to length of I, which defines the probability. Because if I take the summation, means if I take the probability of omega, in that case the length of this omega is going to be 1. So we can very easily find, we can very easily check whether this definition satisfying all the axiom of the probability or not. Okay, so this definition or this approach to assign probability of an event is not depending on those two assumptions which, or those two limitations which were there for the classical approach. Here we are not considering that all the sample points or all the elementary events are equally likely. We are not considering that, and as well as we have an uncountable set in my hand for the sample space. So in this approach, we have overcome both the limitations which we had in the uh, classical approach to assign the probability of an event. Okay. So the third approach to assign the probability is the subjective probability. This is something which is different from the last two approaches. So in the classical and statistical approach, we are actually finding the probability mathematically. We are quantifying those things in terms of numbers or areas or the things we are measuring in this manner. But in this case, in the subjective probability, we do not quantify the events, or we do not count the favorable outcome of an event or something like that. In this case, the probability of an event is totally depending on the person who is determining the probability. So subjective probability is based on the feelings or insights of the person who is determining the probability. Okay. So it comes from the person's intuition or reasoning. Intuition or reasoning. It is basically based on the accumulation of knowledge, understanding, and experience stored and processed in the human mind. So basically, it is depending on three things. So one is knowledge, and second is understanding, and the third is the experience of the person. So these three things together with some kind of analysis of these three things in the human mind actually helps the person to define probability of an event. Sometimes it becomes a guess, or sometimes it can potentially yield a accurate probability also. For example, we can think of those experiment where a physician assign the probability to the life expectancy of a patient suffering from a critical disease. So if a person who is suffering from very critical disease goes to a doctor, then the doctor assign the probability of life expectancy of that patient. Those things, that probability is not which is coming from the definition related to the mathematics. It comes from the experience, knowledge, understanding, everything of that particular doctor, and that probability can vary from person to person. So the probability of life expectancy of that patient given by one doctor can be different from other doctor also. So this subjective probability, which is uh, given by the person or the decision maker, is something which is different from the mathematical definition, that classical approach or statistical approach. Okay, so let us go to the next topic, which is related to some mathematical analysis of this probability theory. So here we have the first theorem. The first theorem says that if we have a probability space as omega, script s, and p, then probability of complement of a event A is equal to 1 minus probability of the event A. So how it is happening? It's very straightforward. So we have A union, sorry, I should have A union A complement is equal to omega. So then these two events, A and A complement, are mutually exclusive also, and they are exhaustive actually. So A union A complement is equal to omega, represent these two sets are exhaustive, and A intersection A complement will be mutually exclusive. So from the second axiom, we have probability of omega is equal to 1. And for the third axiom, we have the probability of A union A complement will be equal to probability of A plus probability of A complement. So if I add, means combine these two things, we have probability of A union A complement. Probability of A union A complement will be equal to probability of omega is equal to 1. And probability of A union A complement by the third axiom will be probability of A plus probability of A complement. So together we have probability of A plus A complement is equal to 1, which represent probability of A complement is equal to 1 minus probability of A. So there is a mistake here. So probability of A complement is equal to 1 minus probability of A. So this should be A complement. This should be A complement also. Okay. So this is the first theorem of basic elementary theorem of this probability theory. So from here we can conclude that probability of any event will lie between 0 and 1. So from the first axiom, we have probability of any event is greater than equal to 0. Now from these we can see that probability of A will be equal to 1 minus probability of A complement. Now probability of A complement is also a probability of an event, so this is also greater than equal to 0. So this is also greater than equal to 0. So 1 minus something greater than equal to 0 will actually reduce, which is means this probability is less than equal to 1 then. So probability of A is greater than equal to 0 and probability of A is less than equal to 0. So together probability of A will be between 0 and 1. The second corollary says that the probability of phi is equal to 0. How it is happening? So we know that probability of omega is equal to 1 and probability of phi, which is probability of omega complement, is going to be 1 minus probability of omega. So this will be equal to 1 minus 1 equal to 0. So as null set is the complementary event to the whole sample space, so probability of phi is going to be probability of omega complement, which is equal to 0. Here, two things should be observed, that those are the remarks I have mentioned here. So the first remark says that the probability of any event equal to 0 does not imply that that event is null set. Okay, that means probability of A is equal to 0 for some A belongs to script S. We call A is an event with 0 probability or a null event. However, it does not follows that A is equal to phi. It does not follows. So we may have some scenario, we may have some events which contain some sample points, but corresponding to it, the probability is 0. But it does not mean that the set is an empty set. It contains some sample points. Similarly, if I have a event B for which the probability of the event is 1, that does not mean that B is equal to the sample space. B is the only subset of B is the only set of all possible outcomes. We may have that kind of scenario also, where B is a certain event because the probability of the event is equal to 1, but it does not follows that it is going to be omega. Okay, so we'll go to the next theorem. So let me just erase this thing. The second theorem says that if you have a probability space omega, script S and P, then for any two event A and B, if A is a subset of B, then probability of B minus A will be equal to probability of B minus probability of A, and probability of A is less than equal to probability of B. So again here also we have very straightforward proof. So I have A is a subset of B. So let me just visualize it, then we'll go for the proof. Suppose I have the sample space A here. So I have set B and I have a set A here, which is inside B. A is a subset of B. Okay. Then if I want to show that probability of B minus A means I am talking about this portion which is outside A, the portion of B which is not containing A part. Excluding this A, I am talking about the B part. So if I think about this B minus A, then to find that probability of that event, we can think of B first. We can think B as union of A and B minus A. And this A and B minus A are mutually exclusive. So we can think that probability of B is equal to probability of A union B minus A. Now, interestingly, A and B minus A both are mutually exclusive sets. So, by axiom 3, we will have probability of A union B minus A is equal to probability of A plus probability of B minus A, because they are mutually exclusive. Okay. So from here we'll have probability of B minus A is equal to probability of B minus probability of A. So it's very straightforward from this diagram also. And also, if we have this thing, probability of B minus A is equal to probability of B minus probability of A, then we can very easily verify that the probability of B is going to be greater than equal to probability of A, because the probability of B minus A is a probability measure on the event B minus A. So this probability is going to be greater than equal to 0 as per my first axiom of axiomatic definition. So this is greater than equal to 0. So this is greater than equal to 0 means probability of B is greater than probability of A. So this theorem also very helpful in many places where we need to find the elementary probability of certain event. Okay. So now let us go for the next theorem, which is a very important theorem in probability, that is the addition rule. So addition rule says that if I have two events A and B corresponding to a probability space, then probability of A union B is going to be probability of A plus probability of B minus probability of A intersection B. So here one observation is that if I have A intersection B is equal to 5, that means if we have mutually exclusive sets, A and B are two mutually exclusive events, then A intersection B becomes 5. That means probability of A intersection B is going to be 0. Then this part becomes 0. So the probability of A union B is going to be probability of A plus probability of B, which is nothing but the third axiom of the axiomatic definition. So it is true there also. So let us try to prove this addition rule for two events. So to prove it, let us try to understand this thing first by using the Venn diagram. What does this theorem says? Suppose I have two events A and B here. So this is A, this is B, and this portion is A intersection B. Okay, A intersection B. So this is my whole sample space, omega we are talking about. So, so in this context, if I want to find the probability of A union B, that means we are talking about the whole region covered by A and B. So if I am to find the probability of this whole region covered by A and B, then I must have to count the probability of A portion and I have to count the probability of B portion. So now if I look into the right hand side, the probability of A plus probability of B will cover all the portion by A and B together. But in this count, we are actually counting this common portion two times. While I'm calculating the probability for A, it is counted once. While I'm calculating the probability of B, it is counting another time. So two times it is counted. So that's why I have to subtract one time to make the balance. So I have to subtract the probability of A intersection B, because this portion is the A intersection. So mathematically, by using the set theory, we can prove it very easily. So to prove it, we have considered A union B as the two mutual union of two mutually exclusive sets. One is A, you can take B also. One is A, and the other part is the only B part. Only B part means B minus A set. So similarly, you can take the B union A minus B also. The similar process will be there. So let us take this in this manner. So A and B minus A are going to be mutually exclusive events, or they are disjoint. Now by third axiom, we have that probability of A union B is going to be probability of A union B minus A. Since they are mutually exclusive, I'll have probability of A plus probability of B minus A. Now, to prove this thing, we have just manipulated something. So here we have considered probability of A plus probability of B minus A plus probability of A intersection B minus probability of A intersection B. So I have added ones and subtracted ones. Now, if I think about this thing in the bracket, the probability of B minus A, we know that B minus A is nothing but B intersection A complement. So I can write probability of B intersection A complement union A intersection B, because these two set B minus B intersection A complement and A intersection B, A intersection B and A complement intersection B, they are mutually exclusive. So again by maximum 3, I can go in the reverse manner also. I have probability of a set plus probability of another set which are mutually exclusive. I can write probability of that set A union another set B. So here I have written that part. So probability of B minus A, which is B intersection A complement, plus probability of A intersection B will be equal to probability of A complement intersection B union A intersection B. Now, if I join these two things, it is nothing but this. So this thing is can be written as A complement union A intersection B. So this will actually give us omega minus, sorry, omega intersection B, which will be equal to B according to the uh, set theory. So this whole thing becomes B. So I'll have probability of A plus probability of B minus probability of A intersection B. So this is the addition rule. Okay, so addition rule actually helps us in many places to find the probability of some elementary events where we have two events for which the probability is known. In that case, we can find the probability of the union of those two events by using this idea. So if we have three events, then we can generalize that thing like probability of A union B union C. This will be equal to probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of B intersection C minus probability of A intersection C plus probability of A intersection B intersection C. And this thing can be generalized as this thing is generalized by using this is called general addition rule or the principle of inclusion and exclusion. So here, if you look into this pattern to find the probability, we have the probability of A union B union C is equal to sum of the probability of individual events minus sum of the probability of intersection of two events together and plus probability of intersection of all the three events. So in general, if I have n number of events, then the probability of union of all those n number of events will be equal to summation of probability of individual events minus summation probability of intersection of two events taken together, and then plus I have to take three events, intersection of three events together, and so on. The final term will be minus 1 whole to the power n plus 1 or minus 1 whole to the power n minus 1 uh, into probability of intersection of all the n events. So that will actually gives us the probability of union of the n number of events. Okay, so let us go for some example where we can use this addition rule to find the probability of an event. Let us try to illustrate this by using following example. So example is that a die is rolled twice So let A be the event that the first throw shows at most 2, and the event B is that the second throw shows at least 5. So at most means less than equal to, and at least means we have greater than equal to 3. Then what is the value of probability of A union B? So basically, if I think about the set of all possible outcome, which is omega, then there are 6 to the power 3, 6 to the power 2, because I am rolling the die 2 times. So if I roll a die one time, then the number of possible outcome for that experiment will be equal to 6, because 6 possible outcomes are there, 1 2 3 4 5 and 6. So if I roll the die 2 times, I'll have 6 into 6, that is 6 square equal to 36 possible outcomes are there for rolling a die 2 times. Now the script is going to be set of all subsets, set of all subsets of all subsets of A. This will be the set of all possible subsets of A is the sigma algebra corresponding to this. So we can think this as power set of A also. Now my A is equal to the all those pairs. So basically this omega contains the pairs. The first pairs, like it means the pairs like 1 1, that means the first row shows 1, the second shows 4, second row shows 1 again. So if both the throw shows 1, then I will have a pair, that is the first element of this sample space omega. So if I consider this A is the event which contains all those pairs for which the first element of the pair is at most 1. That means it could be 1 or 2. So if I think about this, then what are the possible what are the favorable outcome for this A? Let me write down that thing. The first row throws 1, second could be 1, first 1, second 2. So 1 3, 1 4, 1 5, 1 6, 2 1, 2 2, 2 3, 2 4, 2 5 and 2 6. These are the only possible outcomes which are in favor of A. So you can see there are 12 possible outcomes. So I can write cardinality of A is equal to 12. Similarly, B will have those pairs for which the second element of the pair is at least 5. That means the number is greater than equal to 5. So I can have 1 5, 2 5 and so on up to 6 5. So there are 6 possible things. Similarly, I'll have 1 6, 2 6 and so on 6 6. So there are B will contain 12 possible outcomes. The cardinality of B will be equal to 12. Now, if I want to find the probability of A intersection B, I need to find what are the elements of A intersection B. Now, if I find that A intersection B is 5, then the probability of A union B will be simply the probability of A plus probability of B. Now, let us check what are the elements of A intersection B. So, we can observe that 1 5 is an element which is common in A and B, and we have 1 6 here, 1 6, we have 2 5 here, they are common, and 2 6 are there. So 1 5, 2 5, 1 6, 2 6. So these 4 elements which are common in A and B. So the cardinality of A intersection B is going to be 4. So now let us find the probability. So probability of A is going to be 12 divided by 36. By the classical approach, we have the probability of A is equal to number of favorable points, sample points for A divided by total number of sample points. So total number of sample points is 36. The favorable number of sample point is 12. So 12 by 36. Probability of B will be equal to 12 by 36, and probability of A intersection B is going to be 4 by 36. So I have these three things in my hand. So if I want to calculate probability of A intersection B, probability of A union B, we want to calculate this thing. Probability of A union B, that will be equal to probability of A plus probability of B minus probability of A intersection B. That is the addition rule, whatever we have in my hand. So this will give me 12 by 36 plus 12 by 36 minus 4 by 36. So this will be 24, 20 by 36, which is 5 by 9. So the 5 by 9 is the required probability for this event, A union B. Okay, so let us stop here. So today we talked about the probability assignment approaches, the classical approach, statistical approach, and the subjective approach to assign the probability of an event we talked about. Then we talked about two elementary theorems, and then we talked about the addition rule and inclusion exclusion principle. We have seen some examples related to the addition rule also. So all these uh, all these things was prepared, or this slide is prepared from two of the books. We follow these two books. One book is uh, Gupta and Kapur, Fundamentals of Mathematical Statistics, published by S. Chand and Sons. And the other book is Rohutki and Asanes Saleh, which is an introduction to probability and statistics. It is published by Wiley Publication. So these two books are mainly followed to prepare the content of these lectures. So thank you all. Thanks for watching. Bye bye.